Simon. Also, thank you, Adil, for giving me the opportunity to talk here. And yeah, I'm trying to combine the principles which we heard about in the first talk and in the second talk, and then talk about assemblies in curved space and the implications, what we can learn from them for self-assembly in Euclidean space. And I want to quickly start with like the vast majority and vast field of self-assembly and what we can do nowadays with colloidal self-assembled structure. So when I talk here about self-assembly, I mean self-assembly of colloids and on the nanometer to micron scale. And nowadays we have so many different ways to synthesize them with different interactions, with different shapes. And especially shape is the thing I'm mostly interested in. But you can think about, which is usually like the most fundamental way of tuning interactions between particles. You can then add them to the surface and can add like ligands or DNA, what we saw in the previous talk. And then, of course, you can think about, like, for example, this temperature protocol is like a external way of then creating different kind of crystal structures, but you can also think about them if you have them on surfaces and so on and so forth, and you can get a lot of different crystal structures based on them. And also nowadays, this is not only a theoretical idea or an idea for simulations. Nowadays, we can also synthesize a lot of different crystal structure or particle shapes, the fundamental building blocks. We can functionalize them and make them patterned. We can branch them and so on and so forth. However, in my talk here, I want to first really focus on hard particle self-assembly, so where we only have shape, because even if you only look at this assembly where you're not allowed to overlap the particles, so it's purely interacting via excluded volume, you get still a plethora of different and even very complicated crystal structures. So you can think about hard sphere particles, which form the XCC structure. But if you deform them, if you give them different facets and so on and so forth, you can get really, really complicated structures with multiple local environments for each particle. You can even get, and that's what Michael showed last week, the quasi-crystal, which has like a multitude of different local environments, or even crystals with unit cells, like hundreds of particles within a unit cell, so a very, very high degree of complexity. The biggest question, however, is if you have a certain particle shape or building block, it's often really, really complicated, or it's hardly feasible to really predict what kind of crystal structures they form in the first place. So, and the question also is, why do some of the particles form these very elaborate and complicated crystal structures in the fundamental level? Why is that the one which tries to minimize free energy? And why are some really simple, like, for example, the FCC structure? And that's even already pretty apparent when you think about maybe one of the most simplest shapes apart from spheres, the Platonic solids. Because here you can see that they form like also completely different structures, and predicting them just based on the shape is quite complicated. You could think about, okay, maybe they do something which is based on the packings, but what Rosie last week showed is that the packing signature doesn't really occur in the self-assembly where you maximize entropy. And here you can see that some of these particles exactly have these kind of very simple crystals, form these simple crystal structures like FCC or the rhombohedral structure. And we have also candidates with the quasi-crystal or the beta manganese, which have multiple local environments. So how can we get more information about this and about why they form these kind of different crystal structures? And for this, I looked at the special case, in my opinion, which is the cube. The cube has a crystal which packs perfectly, so 100% packing fraction in their packing. However, they also form the same structure when you self-assemble them, so when to try to maximize free energy. And that makes intuitive sense, because also in entropy, this phase alignment is in terms of the entropic forces, or these effective forces, is also very, very likely and also favored, which means that the simple cubic phase has not really, can form these without any global frustration, which means that this crystal structure is not, also in the assembly, is not really geometrically frustrated on the global scale. So they can produce what they want to do locally also on the global scale. But so can we use this and now try to bring the other shapes into a similar condition like for the cube? So basically, here comes the idea to introduce curvature of space into the system. So basically, what you want to do is you want to make these kind of shapes theoretically perfectly align with each other, such that they don't form any gaps. In 2Ds, you can think about, like, if you have a set of triangles and you want to make them fit together, what you do is you just introduce the third dimension and you pop them out of space, and then they fit perfectly together. And you can think about the same concept in 3D, where you just have a curved space around it, such that all these gaps then make a perfect fitting packing, basically. And interestingly enough, or that's really nice, that for all of these other platonic solids, we can identify in curved space exactly these kind of tessellations, where the particles perfectly tessellate the space. So here I illustrated them, and I have exactly the same issue like Jonathan, for example, where I try to somehow visualize them. So these are all projections of a tessellation in curved space and then into Euclidean space, and then here on the flat screen, which means that for the octahedra, we can identify a tessellation which is made out of 24 cells on the hypersphere surface, so in S3. And here, because of the projection, it looks like there are smaller octahedra and larger octahedra, but all of them are the same size. It's just distorted due to the projection. And the same thing you can also do for dodecahedra, where you have the 120 cells, or 120 dodecahedral cells which tessellate the S3. And for tetrahedra, you have the 600 cells. So these are 600 tetrahedra which tessellate space perfectly. You also have for icosahedra, where you don't have go in S3, but in H3, the icosahedral honeycomb which tessellates space completely. This means that in these kind of assemblies, or in these kind of spaces, we theoretically have a optimal arrangement of these particles, and also globally you don't have any frustration. So the question is, can we use curvature now to regulate the geometric frustration to obtain locally optimal environments, also in self-assembly and not only in packings as we can see them here? And for the rest of the talk, I also will only mostly focus on the tessellations and S3. So you can think about this also very intuitively. If you go back to 2D, there are lots of studies now where you introduce curvature just the other way around, where you have something which tessellates or which packs really nicely in flat space, but what happens if you curve the space and add Gaussian curvature to it? So here's a study by the Chaikin group, where they then analyze how the defects form, because defects have to occur to accommodate the curvature. But here, of course, you have the triangle lattice. What happens if you have different type of lattice, like, for example, a square lattice? And when you curve the space, or if you have a PhD student who wants to keep, like Debbie, she's curving the space and put, for example, cubicle or square tiles in there. And you can see that it also introduces defects, but in a different way. Yeah.
Or the triangle. When you said defects, what do you mean by defects? Because
So
you
defects.
have a triangle of this. You could do that like I said, but just bigger, so just we got 5 triangles next to each other, but then the rest gets 6.
Exactly. That's one. Like you get these disclinations in your lattice structure. But here you can also see that depending on the curvature, they either form like single disclinations or scar patterns. So there are different ways how they accommodate the curvature. And the same thing happens in squares. And if you have more questions, ask Gabby. She knows everything about it. The whole idea, however, if you go to 3D or 3D systems, are not new. There are lots of people who already looked at this in the late 70s and early 80s, and the names have been already mentioned by Jonathan. Like Sadok and Mosseri and Sethna, for example, who looked at them in different concepts to understand the local environments, for example, in glasses or in some of Lave's phases or in the A15 phase. Also, people looked at them to understand tetrahelices and these kind of packings on a cylinder, or like we have already been told about in the very first talk in terms of liquid crystals. And interestingly enough, in the last couple of years, so since 2013 and 20, these have been nowadays more and more adopted again, and we saw this illustration already. But also in these other types, like for example, tetrahelices, to understand the formation of these kind of spirals, or in terms of understanding the local environments of Frank Caspar phases. This kind of concept has been looked at, but only for sphere systems. So what happens now if we introduce this other also shape into the account? And to understand colloidal assembly, I perform Monte Carlo simulations, and want to, with these Monte Carlo simulations, try to ask 2 different questions. So first of all, are tessellations also entropically favored, not only in terms of packing, but also entropically? And then what can we learn about self-assembly in flat space from curved space? So my Monte Carlo simulations look like this. So this is the illustration in the equivalent in 2D, where I place my particles on the surface of a hypersphere, so in S3, and perform these kind of Monte Carlo move, and then it slowly reduces the hypersphere radius by applying a pressure to it, such that it slowly compactifies, and then see if it crystallizes into a certain structure on the hypersphere. And so let's start the first question. What happens? Are they also favorable in curved space? And here I start with the heart of the dodecahedra on the hypersphere. And so to see if the 120, so the perfect tessellation is also entropically favorable, I put 120 dodecahedra on the hypersphere. And what I can see both if you look here at the video, so this is the simulation, you can see that first it is in a gas phase and randomly distributed, but at some point it will go into a crystalline phase, which can be, if you compare this one with the perfect 120 cell packing, you can see that it goes into this 120 into the 120 cell. Yeah.
So obviously, depending on volume, the angles are changing. So when you say you're packing those, you pack the centers and you allow it to expand until it fits.
So yeah, you could do it either way. So how I do it, I pretty much reduce the curvature of this or increase the curvature of the space, basically. I go from a very large hypersphere radius.
You have a target curvature.
Exactly.
Okay.
Yeah.
Pieces. So are the shapes changing necessarily then?
Yes. So these are always spherical shapes, so the shapes change according to the space itself. Yeah, that's true.
Okay, so just the way the picture seemed to suggest that you had small and plenty of space in between. So there's a target curvature built into your little pieces.
So it's, yeah, so each, exactly, due to the tessellation, that's the target shape basically they wanna adopt. But depending on the radius and the pressure pretty much I apply, they will have gaps in between. Exactly. And so basically what I can see is that you get like a nice first order phase transition. And also if you look at the G of R, so the pair distribution functions both of the center of the particles, this is this one, and the vertices of the particles, you can see that it nicely goes into these characteristic peaks of the 120 cell and of the dual cell, which is the 600 cell for dodecahedra. What I can also see is that the positional order occurs before you see rotational order. And that makes sense because there has been already previously in the 1990s studies of these kind of Monte Carlo simulations of spherical particles, and you can see that for spherical particles they also of course want to adopt this 120 cell structure, which means that if the sphere is also likely to form and transition into this system, makes sense that you also get a rotator phase in that structure. Okay, so we can also look at hard octahedra. So here we do the very same thing, but we have the 24 cells, so we have 24 octahedra into this in the system, and we can see that they also transition into into the crystal structure or this tessellation. And you can also see this from the radial distribution functions where it's self-dual, so you get the same peaks. What you don't see is like a nice phase transition, but this has probably something to do with that we're only dealing with 24 particles, so it's very hard to obtain the phase transition. And lastly, the tetrahedra. Here we can see something really interesting. So it also, according to the radial distribution functions, it goes into the 600 cell configuration with these peaks, and here the dual peaks of the 120 cell, but we can't really reach perfect tessellation. So what you can see is already that it's like slightly distorted and so on and so forth. And when you zoom into the structure, you can see that it forms these kind of void defects in this system. So there's like slight voids which form during the transition, which can't be then solved anymore. And I looked at this by varying the number of particles. So I did the same simulations just with a different number of particles. We can see that for octahedra and dodecahedra, like the lowest volume per particle you can get for exactly the 120 and the 24 cell case. But for this, for the 600 cell, the lowest happens around 580 to 590. So there's a small mismatch to the ideal configuration. And you can also see this when you, for example, when I show here the simulation with 580 tetrahedra, so where there's 20 particles missing, you can see that the peaks are way sharper than for the 600 cell case. And also when you see the transition, you can see that it's way more, way denser. You can then compact or.
Do you have an idea where I'm going to joke. Suppose it's 588 that works. Where the 12 missing ones are.
So the 12.
I'm joking a little bit. But suppose 588 was the number of gaps that it's supposed to be. Never mind.
The issue is just that you might have a place where a tetrahedron should be, but it can't reach.
Yes, exactly.
It's still like the 600 cell configuration. just has some holes that are.
Exactly, it has some holes and some like interstitials, which where there's not supposed to be. And you can also look at like to understand why this happens is I looked at which pressure does the phase transition occur. And you can see that at 580 it already occurs, which means that the vacancies help the system to enter this crystal phase earlier, and then afterwards, if it's so compact, it can't really resolve it anymore, and therefore you can't get the perfect the perfect tessellation basically. And this is really reminiscent of the square case again. So Marla and Dijkstra did these simulations and also observed that at the phase transition, vacancies help to transition into the simple cubic phase way earlier than for the than if you don't have vacancies. And this is because you have like these kind of linear modes where you can slide a square up and down. And we have the same thing in the 600 cell, because the 600 cell is comprised of also these kind of tetrahelices, which you can also slide. So it's an analogous system both for the tetrahelices and for this these cubic phases.
Big question. I mean, that's an interesting comment there. Is there a way that you can actually detect that mode in your simulation?
So in terms of this kind of sliding,
yeah, looking at kind of correlated to see whether that's true. Because I said, yeah, I just want to measure that.
So you can measure like the displacement from the ideal configuration to see that it's like
kind of coordination motion along the great circle.
Yes, exactly. So it's pretty much that the particles are also very likely to switch between two sides.
Yeah.
Which means that so they're often not collectively moving all in one direction, but it's more or less like you have an interstitial, and therefore it's easy for them to just position themselves in between two lattice sides.
So that if you say that you get along these
exactly. Exactly. That's exactly true. So and then you can do free energy calculations to see which I also did to see that these kind of vacancies that there is like for the 600 cell a certain amount of vacancies which are more favorable exactly at the phase transition, such that they effectively at a certain density should die out, because like I said, it's very complicated how to resolve them again. That's the reason why we see the crystal this defected crystal structure. Okay, this is pretty much the first part. So we can have now a basis that we know, okay, these kind of tessellations are also entropically very favorable. But what can we now learn from this in Euclidean space? So basically, what we want to do is use this as the basis and then now slowly go into Euclidean space. And how do we do this? We do this by pretty much changing the number of particles. And why do we want to do this? Well, if we, for example, look at the dodecahedral case, and we know that it wants to form a free energy beta manganese structure, we can already see that some of the signatures, for example, in the G of R, if you compare here the 120 cell in red and the beta manganese structure, if you compare them, you can see that most of them already nearly fit together. And if you increase the number of particles, which means if you keep the density constant, but add more particles, which then effectively increases or decreases the curvature, you can see that these kind of these peaks get even closer and closer. So yeah, this is pretty much the relation between the curvature and the number of particles if you keep the density constant. And like in the two-dimensional case, now the system have to introduce defects into the structure such that they can't really perfectly tessellate space anymore. Okay, so let's go through the whole all the systems. And so here, how do I quantify these kind of different local environments in the system? What I'm using here are the Minkowski order parameter, which are a weighted Steinhardt order parameter, which means that I pretty much quantify the symmetry around each particle. And what I do is I look at the particle and then create bonds between their nearest neighbors according to the Voronoi tessellation, and then see how they, and then quantify them according to this Minkowski order parameter. And here I have now simulations lower than 200, and this is for the dodecahedra, so which forms tessellation 120 cell. So this is just a small amount of, or you deviate to, like a small amount from the ideal curvature. And what you can see is that many of the particles still want to occupy the space, which is the perfect 120 cell environment down here, or up here. But some of them already form defects or like environments which are not compatible with the 120 cell, and they reach into this regime, which is also, and here this white line shows you where the region where the beta manganese structure occurs. And if you increase that more and more and more, you can see that effectively the shape doesn't really change of this cloud, which means that it always has like some contingent of particles which try to be very, very close to the 120 cell configuration, and some which deviate, which can be then defined as the defect structures, basically. And interestingly enough, you can also see that so beta manganese has two different local environments with the two different Wyckoff sites. And if you compare them, this one and this one, so this is 8C and this is 12D, you can see that in the Minkowski order parameter space, 8C is closer to 120 cell than 12D, which means that you can you can pretty much think about one of them as the local environment which they try to obtain, so the perfect local environment, and the other one as the defect that you add to the system. And to quantify this a little bit better, I have also during the increase of particles, I compared which particles, if you have a local environment like here, is it closer to 8C or to 12D? And based on this, you can see that it then slowly integrates more and more of these kind of defects until you get the ratio that you would expect from the beta manganese structure. Which means that, yeah, one is 120 cell like Wyckoff site, and the other one is the defect Wyckoff site, basically. So let's go to the next example, the 600 cell. Here you can already see, if you compare the ideal quasicrystal to the 600 cell, you can see that if you only have, so this is again the 600 cell, that these kind of voids and interstitials that they have to integrate already pretty nicely fit with the local environments of the quasicrystal, which means like this kind of phenomenon that it's really easy to integrate void defects and interstitials into the particle has something to do why it helps the system to form these kind of quasicrystalline crystalline structures. And you can do the same analysis where you break it down to like systems which are smaller, or where you only add a small amount of additional particles. You can see that there are still particles, or most particles try to stay really close to the ideal 600 cell environment, but it then branches out into this regime, which is again defects that you put in. And if you increase the particles even more, and here I also have like a small simulation, you can see that this kind of face-to-face alignment is still very present in these kind of in these kind of systems where you get like these kind of pentamers that which Michael also talked about, which are essential to form the quasi-crystal structure. And yeah, and if you go even further and further, you can see that it always has the same shape, and it stays always true to this kind of, okay, close to the ideal environment and branching out to the other environment. But now the question is this true for all of the particles? And if I phrase that the question like this, then it's probably not. So if we now look at the octahedra, which forms the like a rhombohedral crystal, we can see a different tendency here. So if you have the 24 cell and add a couple of particles, for example, 36 cell, you can see that you still get like this kind of face-to-face alignment, which then also still favors like something which is very close to the ideal 24 cell, and then again branches out into this region, which can be then again seen as the defects. However, if you go further than around 50 particles, you can see that suddenly the system, and I think this is again a video, the system detaches from this region. So, and here, which means that in these kind of systems, the particles, none of the particles try to obtain the ideal configuration anymore, the ideal local environment. So what they do instead, and you also don't really see in these kind of systems anymore this face-to-face alignment. So what they do instead is they try to form all one single environment, which is here the rhombohedral crystal. So instead of trying to keep the local environment for some of the particles the same and then having interstitials, what they do, they try to resolve the geometric frustration just uniformly, and each individual particle is trying to do this. And yeah, and if you increase the number of particles more and more, you can see that it goes towards the direction. Okay, so now we know like maybe the fundamentals, that there are some crystals which we can think about, oh, they minimize free energy because they can be seen as defect structures of the tessellations, and some of them which are doing this uniformly because the curvature mismatch is too large, so this whole mechanism breaks down. And I see this breaking down a little bit similar to what Greg talked about last week in terms of these kind of mechanisms in frustrated self-assembly, where you have particles which try to have a local environment which is incongruent with global configurations. And therefore, if you can think about this here, this self-limiting case where you have like some particles which have defects in it, as the regime where you have like just a small curvature mismatch between the Euclidean space and the space which tessellates the hypersphere. But at some point, the curvature is just breaking down, and then you get this frustration escape where it's just surrendering basically, and just takes the configuration which fits the space itself. And that's what you can pretty much see here. So you can see that if you space curvature, so this is just like a sketch, where if you increase the curvature more and more and more, you would eventually get into this frustration escape regime. And you can see that for tetrahedra and dodecahedra, luckily for, I don't know, crystallographers and so on and so forth, they don't reach this frustration escape when you go into flat space, but for octahedra, that's what happens. But now the question is, again, what is the like a really nice connection between them? And maybe also for the future, how can we now use this kind of information to maybe create new materials or other materials which are created based on, for example, on the 24 cell. So how can we pretty much increase this window and or move this line such that, for example, the 24 cell still wants to do this. And this is like a little bit of I wanted to start a discussion. So how can we do this? I thought about maybe combining this with a little bit of this, such that you have a shape which is not hard anymore, but can deform a little bit. So the interactions might be hard, but the particle itself can deform a little bit, where you give the particle shape a certain energetic penalty if it deviates from, for example, the octahedra. But this would give the whole system another way to resolve geometric frustration, such that a combination of deformation of the particle and relaxation or stiffening into flat space would broaden this kind of window and going and such that you can create these kind of other materials maybe. People, like I gave this talk a couple of times, so they always ask, what about the icosahedra? Icosahedra is not as easy as I already mentioned, because there you have to do simulations in hyperbolic space, and it was already hard enough to do all the math in spherical space. But effectively, you have to go into hyperbolic space, because here you have like the perfect, you have a gap angle where you pretty much, if you overlap them all, there would be like small little overlaps. So to resolve them, you have to go to negative space to make them perfectly aligned. But the interesting thing, if you look at icosahedra, is that you can see very like already also hints that you also see in the octahedral system. So if you compare the ideal icosahedral honeycomb, the FCC crystal, which it usually forms, and like the typical local environments of the FCC self-assembly, you can see that it really looks rather similar to what we saw in the octahedra. So it hints towards that there's also a frustration escape in the icosahedral case. So everything tends towards these kind of systems. And I don't know if I might be a little bit fast here, but this is pretty much what I wanted to talk about. So basically, these two questions I could answer. First of all, yeah, tessellations are not only ideal in terms of packings, but they seem to be universally also ideal in terms of free energy minimizations. And I also could show that the curvature, the space curvature, can be seen as a tool to regulate geometric frustration. And I also had an answer to question 2, that self-assembly in curved space reveals like in terms of the fundamental physics, 2 different types of assemblies. The first one, and these are the very more complicated one, where you have multiple environments, are tessellations which are remnants of tessellations in curved space. Examples are the tetrahedra or the dodecahedra, where I saw the beta manganese and or can identify beta manganese in the quasi-crystal as defected tessellations. And we have assemblies that minimize free energy uniformly, which are, for example, octahedra and icosahedra, where we saw this geometric this frustration escape. And yeah, with this, I want to thank Sharon Glotzer, and especially also Xiaoming Mao, which is in the University of Michigan in the physics department, Kai-Sun as well. Gabby, of course, as well. The whole Glotzer group, my funding, and all the software we developed in the Glotzer group. So all the simulations were done in HUMD. And if you have questions about HUMD, we just released version 4 with new different things. The API has a little bit changed, and I'm now a maintainer of HUMD Blue. If you have questions about it, if you want something to be added to it, please talk to me. and I'm always happy to help and also talk about how we can improve the code even further. And yeah, thank you for your attention and any questions.
That UMD blue,
That's UMD Blue, yeah.
that's just some generic person or program.
Oh, this is called, this is our analysis tool, which is called Freud.
Ah.
So yeah, we have Signac, we have UMD Blue, and we have Freud.
What does Signac do? Why should everyone use it?
Yeah, so okay, Signac is pretty much a project management tool, such that we can run multiple simulations with multiple state points. Often people use just have like a very intricate way of folders and directories, and this is all managing it, such that if you have trying to do simulations with multiple of state points, it helps you to find those state points, to manage them. And also, if you run on supercomputers and clusters, it helps you to submit your jobs really easily. So yeah, there's also, I'm not a maintainer for this one, so don't ask me about it if you want to improve that one. Yeah. Yeah.
So in, of course, in hyperbolic space, things just kind of scaling.
Yes.
Are you working inside of the, like hyperbolic, bring out like a manifold where?
So the idea is to, because it's like icosahedra is tessellating it, I'm thinking about implementing icosahedral boundary conditions, such that you have periodic icosahedral boundary conditions. So to put them into to simulate hyperbolic space, which is then just an icosahedral part of hyperbolic space.
But it's not wrapping.
It's wrapping around. So you have to think about. So the boundary conditions are quite complicated, which means that you would expect. So usually when you do, for example, simulations in Euclidean space, you have like the double torus. You pretty much simulate it on a double torus, and using instead of a cube. An icosahedra could help you to realize simulations on in hyperbolic space.
So what kind of saying is that there's a spherical icosahedral space.
Yes.
Where you twist those.
Yeah, you have to twist exactly.
Hyperbolic where you twist a little more.
Yeah.
So
there's a whole variety of things where you have an integer number of icosahedra.
Yeah. That's one of the single ones.
That's true. Yeah,
that's what you're asking.
Also, so it's true the icosahedra doesn't pack S3, but there's a nice tessellation that's closely related to 24 cell with gaps.
Yeah.
I wonder what happens when you throw icos. Like say 24, you have icosahedra in there. So you get sort of try that.
I haven't tried it with like that. I'm aware of the packing basically. So yeah, they also form this kind of packing, but I haven't really went then into in going to Euclidean space again. Because you have gaps. You can think about this like a bidispersed packing, where you can see one particle or the gaps as like a different particle of the gap shape, basically. But I haven't tried it small.
I guess implicitly, so as you increase the number of particles, and they're sort of smaller relative to the curvature.
It is.
I guess it should tend exactly to the Euclidean.
It should also. It should as well.
You were hinting at essentially.
Yes. Yeah. It should as well.
With the way that as you increase the number of particles, you're having on this.
Yes. But exactly. But the thing is that it probably approaches it from the other direction a little bit. Because you go from a more frustrated into a lesser frustrated due to the
And lastly, I guess none of this is within the kind of annealing process. Would that, I guess intuitively that would help you come right in.
Yes. Yeah, you could. This is not with any annealing process. So this is really Monte Carlo just self-assembly and free energy minimization.
Greg, you're going to that questions.
Nice talk again. Again, one each time. Obviously, I'd be very interested in this idea of kind of putting together, I guess, sticky bonds or elasticity, trying to push that gap there. I guess just a kind of a comment. I don't know quite how to do it, but so you might naively think like, well, let's just make these particles sticky and then flexible in some generic way. It turns out that in terms of whether or not the structure will continue to accumulate distortion, let's say, distorted locally preferred structure and or escape to some of these bulk structures is very sensitive to kind of which elastic mode of your structure is stiff, which one is soft. And so it's very soft. It also has the opportunity to distort towards some shape that tiles.
Exactly.
And so, for example, in the kind of puzzle piece model, I think there's an analogy here. You can imagine interactions that favor kind of strong orientational alignment, but relatively floppy as far as distance goes.
Yeah.
Right? And that they tend to, if you like, push the frontier that way. Whereas if you flip it the other way,
it would go in the other direction. Yeah.
So I think there's something also about kind of looking at the normal nodes of these structures and figuring out what interactions are
Would
favor
favor. Sure.
something to think about. Anyway, lots of ideas. So.
Fantastic.
Yeah, I found it really interesting that the dodecahedron and the icosahedron behave pretty differently. If you think back to the talk that Rosie gave, or the picture that I threw up for the icosahedron from your team, basically from those pictures. You see that you can basically cut more and more planes or have transitions between them. So my question would be, if you think about such transition paths between those two, where is actually then the frontier between these two types of behavior?
Yeah, that's a very good question. So I would probably yeah, it's a good question. I don't really know where you have that kind of transition
You have
in
in
between.
the part of the icosahedron, right? You have the dodec, the icos,
Yes.
and then the icosahedron. And the reason I'm thinking about it is also because the icosahedron is usually related with an FCC lattice, right?
That's true.
If basic structures don't really get an icosahedron. So I wonder whether that's sort of the line or if it's just
It's a good question. Yeah, I totally focus on the platonic solids first, but yeah, it's really interesting to see how that might change also that transition in that space as well.
And is it a sharp transition
or not? Yeah. Exactly.
That's a lovely topic.
Thank you.
I mean, well, wonderful talk, Philipp. I'm delighted. So in my very naive thinking, things that want to form spherical Voronoi cells usually form VCC structures, right? Whereas things that want to form small Voronoi cells, they form FCC. So can we learn something from the shape of the as far as the free space tiles of these things when they assemble?
Yeah, that's also like a very good idea to see which one is maybe the one which is in more based on, because in terms of like spherical packings on these kind of curves, you have different references you can go from. Like 120 cell is maybe one is like maybe one of them, which gives you maybe goes then more into the FCC structure. And if you look from the hyperbolic space rather, that this would give you the perspective why certain are forming more the BCC structure. So yeah, so in terms of spherical particles, you have more references than for the shape particles, and that could be the reasoning behind why BCC, for some of them, BCC is more favorable, and some of them more FCC is more favorable. I totally agree there. Even though it's gonna be, because both of them again have the single the single environment, which means that they will be both systems which underwent this geometric frustration, like this frustration escape. However, maybe different structures with different defects have a different escape from the system. So, but I haven't gone too far into that. But yeah, I think it's possible that it's a hypothesis that I can see.
Yeah, maybe another question if I can. So have you got any article where either the packing situation or the entropic situation are very nearly degenerate? So I suppose, is there a particle where, yes, it prefers FCC, but only ever so slightly?
So really only at the highest density.
Yeah, either as a packing problem at the highest density, or if you want even as a I suppose
well, there are like these kind of like even FCC and HCP. This is like already, or if you think about some shapes which have diamond and like this twisted diamond. So there are lots of these kind of shapes which are favoring which are like where the free energy between them is very, very tiny.
Well, and of course there are some systems where you can actually observe the phase transition from one to the other.
Yes.
So as far as my question is, thank you for helping me clarify that. It's what happens if you take one of those systems where you can induce a phase transition between FCC and BCC, say.
Yeah.
You position yourself exactly at the interface.
Yes. And
what
then
happens then when you apply your analysis?
it's a good idea. That would be interesting to see if you can then favor one of them by introducing curvature, either positively or negatively. And I see that is probably the case because
and I think that could push you very close to the frustration escape.
That is true.
If you go slightly on the unfavored side.
Yes.
Wonderful, Philip.
Thank you.
Okay, I think that's a good point at which to thank our speaker once again.